Hello everybody. I will present an exercise dealing with the water flow in soils. And first, a summary in brief will be given about the hydraulic head, water pressure, and flow rate calculations. So the hydraulic head, denoted by H, is a function that quantifies the potential per unit mass of the water when subject to a flow. And the equation of the hydraulic head is the elevation Z with respect to the origin with an ascendant axis plus the pore pressure divided by the unit weight of water. In case there is a difference of the hydraulic head between 2 points M and N, the water flow takes place from the initial point M to the final one, so that the hydraulic head in M starting point is greater than that in point N. And this corresponds to a loss in H, and we can calculate the difference in hydraulic head between the 2 points. That means when the flow starts from N to N, we will have a decrease in the value of the hydraulic head. In case the direction of the water flow coincides with that of Mn, we calculate the hydraulic gradient, I, that is the difference in the hydraulic head divided by the distance Mn. And to solve a water flow problem, it requires first to express the boundary condition, which are of 3 types. First, we have to identify the equipotential lines where H is constant, and second, to precise the imposed flow lines where the water flow is parallel to those lines, and third, to identify the free surfaces where the pore pressure is 0. So the exercise we intend to solve is dealing with a retaining wall, and this is the retaining wall having trapezoid form, and this is a half soil mass that represents the downstream level, and on the left it represents the upstream level, and from the left we have the downstream level. So the first question is, for this case, we need to check that this clay sand layer is subject to water flow, for which we have to identify the limiting equipotential line and the imposed flow line. And we've noticed that this retaining wall is made up of concrete, which is an impervious material because its permeability is negligible. As a reply, considering the hydraulic head equation, we have to notice first that along MA and along MA, not MN, and ST, we have free surfaces because water pressure is 0. And then, considering this equation, the hydraulic head on MA will be the elevation Z, that is H, the height of the retaining wall, plus U by gamma W, but U is 0. So the hydraulic head on this line is H. And along ST line, it will be 0 because the elevation is 0 and water pressure is 0. So, as such, if I calculate HMA minus HST, we obtain H, that is positive. So this difference is positive, then the clay sand layer is subject to water flow that starts from MA and ends ST line. And these are the line limiting equipotentials. Further, along MN and NT lines, the water flow is prevented from the clay sand to the wall. So the water flow is imposed along those lines, and it will be parallel to those lines. And these are the imposed flow lines. Now assume that this water flow we evidenced is in steady regime. That means the flow rate is constant at any time. And considering the assumption that the loss in the hydraulic head between 2 points is proportional to their separation distance. As such, the hydraulic gradient will be constant. So, based on that, question 2 is to determine the hydraulic heads at point M, N, and T, for which we will deduce the respective pore pressure values. So the reply will be, when writing the definition of the hydraulic gradient between M and N, it will be HM minus HN divided by MN, first equation, and doing the same between point N and T, the hydraulic gradient between N and T will be HN minus HT divided by NT. Based on this assumption that the loss in the hydraulic head between 2 points is proportional to the separation distance, so this means I is constant, and equaling IMN with INT, and we substitute the values HM equal H and HT is 0, we can deduce the hydraulic head at point N. Now, using the hydraulic head equation, we can calculate the pore pressure as such. So, at point N, since the elevation is 0, and then substituting in this equation, it will be just gamma W by HN. That gives 10 for gamma W, and this is the ratio B by H divided by H plus B. And also we have UM and UT 0 because they are on the free surfaces. Question 3. Determine the resultant forces of water pressure on the retaining wall, considering the value of H and B, respectively 6 meter and 2 meter. So the reply will be pore pressure at point N using those values will be 15 kPa. But pore pressure is an isotropic pressure. That means it has the same value, and importantly is it is normal to any surface. So along the M facing here, water pressure will be perpendicular, which means it is horizontal. And because U equal gamma W by H minus Z is a linear function of Z, so we can draw this diagram. And doing the same along NT, we will get the distribution of pore pressure on NT that is perpendicular with the same value at point M, since it is an isotropic pressure. So we will have two forces, resultant forces. First is PW, that is the resultant of this diagram of horizontal pore pressure over Mn. And the second is the distribution along NT, which gives this vertical force, UW. So the calculation comes from that a force is the integral of a stress over a surface. So as we can write the two equations, so the result will be simply mentioning that the names of the two forces here is water push force. This force pushes the retaining wall horizontally, while this force UW try to uplift, to make an uplift of the water of the retaining wall. And the calculation will be just the diagram of the two triangular distribution, and it will be half of the base value 15 multiply here by H and here multiplying here by B, and the result will be 45 kilonewton per linear meter and 15 kilonewton per linear meter. So P and PW and UW are forces which are not in favor of the stability of the retaining wall. Now we will try to draw by hand the flow network, considering that we have 3 current tube and 6 interval between the equipotential lines. Then we will deduce the water flow rate at the downstream side, being on the left of the retaining wall, and still using the two values H equals 6 meters and B equal 2 meters. So drawing the flow network by hand using the approximative method. So step 1, we will draw a first current line that forms with the imposed current lines Mn, the facing, and NT, the base, the first current tube or corridor. So on this figure, this is the first current line. I consider it, and between the imposed flow line and this first line I drawn, I will get this space that is like a tube or corridor, right? And now we will, in the second step, divide this first tube in intervals, and the intervals in question are the intervals between the equipotential lines. So this is the first equipotential lines. So if I draw the commencement of this line, not the full line, I will get this curvular form. And doing the same, I will draw the beginning of the second equipotential line, third, fourth, and fifth. And we can count that we have 1, 2, 3, 4, 5, 6 interval between the equipotential lines. So at this stage, step 1, we draw the first current line and the beginning or the commencement of the equipotential lines, because their number is 6. So we have to notice that we can understand that the big value of H is 6 meters here that we have calculated. The last one is 0 here, and moving from this line to this line, because NH equals 6, so the total difference in hydraulic head is 6 minus 0. Okay, and the elementary loss in hydraulic head is the one that corresponds when we move to a given equipotential line to the next. So as we can write here I will have 6 minus 1, that means 5, then 5 minus 1, 4, 4 minus 1, 3, etc. up to getting 0 here. Now step 2 is similar to step 1, so we will draw the second current line, that is dashed line here, and then we will continue the beginning of the equipotential line drawn in the step 1, and then we'll try to continue like this. So there is a mention, an important mention, that is at the intersection point between the current line and the equipotential line, we have to 90 degrees between the tangent to these lines, and this is the mention. At the intersection points, the tangent to flow and equipotential lines are perpendicular. So doing the same, now when we extend the equipotential here, we will get the second corridor or current or tube, flow tube. Since we considered the value 3 for the current tubes, so we have 1, 2, and 3, but you can see that the third current tube is infinite, because our half space here and here is limitless. So now from this drawn network, first we have to check that these width and thickness of this curvilinear squares A and B, A dash, B dash, we need to check the condition that the ratio A by B is equal to A dash by B dash, and we will see why. So now consider this point G to understand what's the merit of this drawn flow network. If I intend to calculate the hydraulic head at point G, so it will be approximated as such. So we can see that, for example, point G has a 0 elevation, Z equals 0, and going to this equation of first for the hydraulic head, we can see that point G is approximately in between this equipotential where H is equal 3 and here it's equal 2. So we can say that at this point we have 15% less than the elementary hydraulic head. So it will be roughly by 2.5 meter. And then, since Z equals 0, the pore pressure will be about 25 kPa. So this is the last purpose of drawing the flow network, is to calculate the hydraulic head at any point. So for the flow rate calculation, this condition implies that we have an equal elementary flow rate in all current tubes. And this is a zoom of a current tube where we can see that when we move from the first equipotential line where we have H, hydraulic head, the next one, the flow, the direction will be H minus delta H. And this is, since we have calculation per linear meter, that means in the perpendicular direction we have the length of 1 meter, and then the flow occurs or take place on this area that is simply A by 1. So to calculate the flow rate in this tube will be just the velocity multiplying the area A by 1. But we know that the velocity is expressed by the Darcy's law, K by I. And as you can see, I here is just the difference in the hydraulic head, that is delta H, divided by the distance P. That is the hydraulic gradient, and this is the permeability. So now delta Q, substituting V by this value, it will be just K delta H A over B. And since we have the number of current tube NC, the total flow rate will be NC multiplying the elementary flow rate for each current tube. So considering the value NC3 and H6 and the total difference hydraulic head 6 meter, and we can calculate just the ratio measuring distance A and B and A dash and B dash. That is for the network I shown, it is about 1.87. So the total flow rate, substituting those values in this equation, will be about 48.5 liter per day per linear meter, since for the retaining wall we considered, we have the calculation for the thickness of 1 meter of this retaining wall. Last question is for which purpose the water action should be taken into account. So as we detailed from the water pressure values, we identified two forces and mentioned that the two forces are against or not in favor of the stability of the retaining wall. So the retaining wall stability depends on the applied pressure by the soil mass, including the pore pressure. Thanks for your attention and see you later.